We're looking at microbial contaminants in the water supply. So this is an environmental kind of application for NASA to make sure that the water that the astronauts are drinking is actually safe to drink.
Now, when you're looking at the astronaut's heart, is it a sensor that you place on their body, or is it something they ingest, or what?
This is an external sensor that will take one drop of blood and be able to screen for a number of different proteins. And depending on the levels of proteins and which proteins are present, we can make an informed diagnosis of the health of the crew member's heart.
Do these sensors have a long shelf life, or is it something that lasts for a short period of time because of the complexity of the sensor?
It depends a little bit on how we fabricate them and how we package them. The sensor itself, without any kind of surface modifications done to it, has a very long shelf life. I have sensors in my lab that are probably 10 years old that I can still pick up and use today. What limits the shelf life of these types of sensors is we often introduce some sort of biological probe molecule on that surface. So depending on what that probe is, that's going to dictate the storage needs as well as the shelf life of the device. We've been placing a lot of emphasis on making probes that are very robust so that we can increase that shelf life for our missions, so that we're not looking to replace these sensors every 6 months, that we can actually keep them for years at a time and continually reuse them.
And one of the coolest things that you were showing us this past week was the fact that you have a cell phone technology adapted to these nanosensors. So you have an application that you developed on the phone that can actually be used in concert with the nanosensor.
So this was designed actually for the chemical sensor project. And this phone has a plug-in port on one side that contains the sensor chip, has a fan that will direct airflow from the environment over the sensor surface. And then just using the electronics that are part of the phone, we have a nice little instrument that will actually read what kind of chemical environment the sensor is exposed to.
Now, would you have multiple nanosensors within that adapter for the phone, or is it just one nanosensor?
So we have one chip, but these chips can be made with a number of different sensors. They can have hundreds of sensors. They could even have thousands of sensors on one chip, all working together to tell the user of the phone what the environment is.
Guys, that was some great information on nanosensors. I can definitely see how that is a game changer, because once it's commercially available, it will definitely change our lives.
I tell you what, we could have spent a whole show on nanosensors. That's how cool the technology is.
That's right, Chris, but we're only scratching the surface at looking at this technology. I had a chance to sit down with Jim Geyer, and he explained how NASA is using nanotechnology to develop better, stronger wires. Let's check it out. Jim, I understand that you're working with carbon nanotubes as a potential replacement for conventional wiring, but I didn't know wiring needed an upgrade. What exactly are you doing to improve wires?
Well, I don't think a lot of people understand that wiring really takes up a large amount of the mass in current spacecraft and aircraft. Like a 747 has nearly 2 tons of wiring in it, and a space shuttle had over almost 300 miles of wire. This is a lot of weight, and so conventional wiring with copper, it turns out is very heavy. Copper is dense, and it's also not very strong. And so we're looking for a way to have a better mechanical properties, actually, than conventional wires have.
So these carbon nanotubes, when you make a wire out of them, how do they perform in terms of strength?
They're much stronger, they're more thermally conductive, so you don't get hot spots and so on. And they're very flexible. They're actually much more flexible than copper, and they don't fatigue. Fatigue is when you get a breakage from moving back and forth.
That's how I break wire intentionally sometimes.
Exactly. And in fact, they ran tests, and they were not able to run enough cycles to actually break these carbon nanotube wires. They finally had to give up and go on to the next test.
Okay, so the carbon nanotubes are stronger and they're lighter. How do they perform in terms of conductivity?
Well, conductivity is the issue. It turns out that carbon nanotubes, while theoretically have a very, very high conductivity, to use them practically, you have to make these bundles, because an actual carbon nanotube is less than microscopic. And so to use them, we have to actually bundle them together. And when you bundle them together, you lose a lot of that conductivity.
And that's principally where your work is then. You're going to solve this conductivity problem.
That's our goal.
Okay.
Right. What we're doing is we are chemically altering the carbon nanotubes. We're doing a process called intercalation, which means to insert. And we are inserting halogen atoms. These are bromine, chlorine, iodine, in between the bundles. And when we do that, it makes the bundles actually much more conductive. And so what we're trying to do is get to the place where our conductivity is high enough that we can run these as electrical conductors. They're not going to be as conductive as copper, but because the wiring in aircraft and spacecraft is not limited by the conductivity, but by the strength, we're going to be able to save a tremendous amount of weight. We're in the early stages of our research, but we've already developed carbon nanotube wires that have a specific conductivity. That's a conductivity per gram equal to copper.
Well, solution, problem solved. That's great. No, that's a good step, right?
It's a good step, but it's not the only step. Okay. Because right now we're working with very, very tiny amounts. I mean, milligrams of material, and we're going to have to work with kilograms of materials. And so we have both the process of our partners who actually make these fibers have to scale up so that they can make large quantities, and we have to scale up our chemical processes so that we can modify them.
Okay, so scaling up is actually the big challenge.
It is.
Okay, see, for a second I thought if I understood this properly, I'd understand how Peter Parker could shoot web. Okay, but apparently with the scale-up issue, not even he could handle it at that.
I'm afraid not.
All right, well, appreciate it. I wish you the best of luck, and I hope soon to see copper wire. Well, I don't want to see them go away, but at least in terms of these aircraft and spacecraft, saving that weight and giving us all the conductivity we need.
I hope so.
It's interesting to see how NASA, as they improve on a technology, just how complex the process becomes. And I never would have thought about it, but creating nanowire is actually a groundbreaking or game-changing technology.
Yeah, and that's a cool area of research that Jim's working on. But another area that NASA's looking at is carbon nanotubes and overwrap pressure vessels. So what they want to do is they want to take a COPV, or a composite overwrap pressure vessel, and spin it with carbon nanotubes.
And those carbon nanotube composites are, as you said, very difficult to work with. So NASA is actually looking at a couple different approaches.
And I had an opportunity to look real closely at least one of those approaches. Let's check it out. We're here with Aslan Biagi, who's the project manager for nanotechnology. So Aslan, tell us about what you're doing with nanotechnology.
Our goal is to actually use the nanotechnology and make lighter materials so that we can reduce weight on the vehicles, on launch vehicles.
And I understand you have a big flight test that you're moving toward.
Yes, so our carbon nanotube reinforcement composites that we're developing in the nanotechnology project will later be placed on a composite overwrap pressure vessel, which will be launched on a sounding rocket.
Haven't we launched like composite overwrap vessels before? What's unique about this one?
So COPVs have been on NASA for a long time. The only difference here is that we're using carbon nanotubes instead of carbon fibers, which is the typical material that we use for the COPVs. Now we're transitioning into carbon nanotubes, and that's actually making the material 2 times stronger than carbon fiber and also lighter. And that's the game-changing part of it.
Tiffany, how do you guys prepare for a carbon overwrap pressure vessel test?
So we start off by taking the tensile strength of ring specimens, where we have an aluminum ring and they're overwrapped with a carbon nanotube yarn and resin and a composite structure. And the reason why we do this is to help us predict the load at where our composite overwrap material is failing. So the rings are speckle painted for digital imaging correlation, so we can better determine how and where the failure occurs.
So you guys actually plan in these tests to actually break the rings?
Yes, we test the bare aluminum rings first so we can get a baseline value of the load where the aluminum ring is failing, and then from there we can subtract the failure from the composite overwrap material from the baseline so that we can know the tensile strength of the overwrap material itself.
Have you done actually any tests? Do you know how successful or how strong this overwrap is going to be?
Yes, right now the first layer of material that we're putting onto the rings fell at about close to a 600 pounds of force from that small overwrap material. The overwrap material that we're testing is only about 0.36 inches wide.
Nice. Mm-hmm. So you do test on rings as well as full tanks, is that correct?
Yes, the tanks are the end goal, but for everything that we're doing right now is for the ring test to prepare for the ultimate burst test, and that's actually when the tanks will be wound with this particular type of material.
You use that word burst specifically because you really want to pressurize the tank to the point of failure, which creates a burst.
Yes, correct.
Yeah. I hope you're successful bursting the tank.
Thank you. We hope that there's not going to be a really large knockdown in properties compared to carbon fiber composites. This technology at this level is still in the premature stages. We're just trying to help do as much research as possible on these preliminary tests so that we can further advance this technology and get it to the area where carbon fiber composites are currently.
So John, Tiffany gets a lot of data from these tests. How are you using that data to prepare for the upcoming flight test?
Well, what we've done is made sure that we've interacted with Wallup's sounding rocket experts to make sure that we capture the entire flight environment and all the design requirements for our COPV and bring those into the laboratory and have Tiffany duplicate the critical environments that the material has to operate in. This gives me data that I then use to size or dimension the COPV, determine how much nanocomposite is actually applied to meet the performance and safety requirements that Wallops has for their sounding rocket flight. We consider the vibration environments and the temperatures that a COPV will see and make sure that all the forces and loads that are applied to the COPV are accounted for in our design.
How will an improved technology, this game-changing technology, help future missions?
Well, we know that the carbon nanotube is one of the most strong and stiff materials known to man. If we can get that material into an engineering application, we could probably make much lighter spaceflight hardware than what we're doing right now. By adding this small nanotube wrap, we could easily increase the strength of the tank by a factor of 2, with only increasing the weight of the tank by perhaps 10%. So that's an enormous gain in strength.
We're back to continue our discussion on the processes to wrap the pressure vessels. We just saw one. Mia, tell us about another.
Okay, so what we've done here is taken a spool of carbon nanotube yarn, and instead of processing it on a large machine, we took the critical steps that we use on a large machine and downscaled the equipment. And so what that allowed us to do is take a small amount of material, get the resin infiltrated in it, and wind either a cylinder or a bottle directly from the yarn.
So essentially what you're doing is you're sort of miniaturizing that process.
Correct. So in order for us to optimize the process using the least amount of material and also getting the process done quickly, normally when we do this type of operation, we use a machine that takes up an entire room. Okay, so we've now downsized that process into a tabletop piece of equipment.
What are the benefits of miniaturizing the entire process?
So several benefits come out of that. One is we basically are tailoring the process that we're developing to the amount of material that's available. We can very quickly rapid prototype in a sense. We can try several different conditions very quickly, changing that using the least amount of material. And also it allows us to modify the machine very quickly to adapt to what we learn as we are winding this material.
When you miniaturize it, are you skipping steps? Because when you look at your device, you don't have many moving parts compared to the commercial
That's correct.
size. And so what have you done to get the same benefits?
Okay, so here are the critical steps, right? You take the yarn, which is dry, and then we need to send it through a bath so that the resin will be absorbed onto the yarn. And then after the resin is absorbed, really what we want to use that infused yarn with is to wind it around the bottle. Okay, so in a very short distance, we're able to achieve that. It's in about a couple of feet, right? We're able to see that process right away.
Now that you have the process that has been miniaturized, what is the next step?
So in order to get our article certified for flight, it needs to be made on a commercial scale. And so those steps that we have defined and optimized are now going to be transferred to a space flight center, which is used to building these types of flight articles. And those basic steps are basically now being adapted back to a commercial machine.
And then from there, that pressure vessel will be transferred to the flight facility where it will be launched on the sounding rocket in 2016.
Correct. We're going to be launching from Wallops, yes.
Now, nanotechnology began several years ago. Well, it's been around for a while, but from where you started with it, how has it evolved over the years?
When we started working with carbon nanotubes, they were still available in powder form. And because on the nanoscale they had such tremendous properties, people thought we could just essentially sprinkle some on a polymer matrix and get the benefit of these materials. We studied it for several years and realized that is not a method that we can get the type of properties that we're looking for, because we're competing with state-of-the-art structural materials, which are carbon fiber composites. So around 5 years ago, we actually switched approach and worked with a vendor so that we use predominantly continuous format of carbon nanotubes. Now, the challenge there is that in the bulk form, it does not have the kind of properties that were existing in the nanoscale. We had to basically optimize the process to take advantage of these processes and work in collaboration with the manufacturer to also optimize those properties from the starting material. So they had to modify their production process to accommodate this. And so there was interactive exchange of information so that we can both get better material properties. In a span of about 3 years, we've made significant advances that take us far from where we started, to the degree that I can say that just 2 years ago we did not have the kind of properties we have now.
And where do you see the future